In this tutorial we're going to talk about the magnetic field in a current carrying wire. And let's suppose we have an infinite current carrying wire, right? And in this case, this has current. And Ampere's law will state, for instance, that the closed integral of p point ds is going to be equal to mu 0, which is the permittivity on free space, times the enclosed current. This is Ampere's law. And Ampere's law is going to be applicable for geometries that are very, very symmetric. It's like applying Gauss's law in electricity, but in this case is to magnetism. And for instance, well, if we see a transverse view of this section, right, we're going to see, for instance, that there is going to be some magnetic field that is going to be traveling around the wire. In this case, due to the right hand rule, well, this is going to be, for instance, anti-clockwise, right? You can put your thumb pointing downwards or into the screen, and you will see, for instance, that you easily close your right hand. Towards the direction anti-clockwise, or in that case it's clockwise. Or for instance, you can state that if the current goes towards the outside, this is going to be, for instance, a anti-clockwise an anti-clockwise direction. We're going to use then this Ampere's law, right? This is we can use Biot-Savart, right? But with Ampere's law it's going to be very easy, because we have this situation, right? And V point ds is going to be V times ds, cosine of the angle. Cosine of the angle is cosine of 0, which is 1, right? And then, for instance, V is equal to it's equal at the same this radial distance. So in this case is the closed integral of df, and in this case the imperial surface, or the imperial arc, in this case is the arc of a circle. So the imperial arc, for instance, is this circle at a certain radius. So this is going to be equal to b and 2 pi r times mu 0 I, and such that b is mu 0 I over 2p radius. So that will tell us that b, which is, for instance, the magnetic field, is going to be equal to mu 0, permittivity of free space, times I, permeability, of free space, times I, which is the enclosed current, over 2p times the radius being, for instance, the distance from the wire to the point of evaluation, right? This is R. So this is the magnetic field due to current carrying wire. This is, for instance, the magnetic field.